Hello, I'm María del Rosario González García. I'm master student at the National Polytechnic Institute at the Technological Research and Innovation Center. My project is thorough powers of the cobaltate of lithium doped with terbium obtained by the Solheim route. The structural, chemical, morphological, and elemental properties of lithium cobaltate doped with terbium at different concentrations were studied. The X-ray diffraction patterns show materials with hexagonal faces and Re3M space group. Rydberg refined verified the incorporation of the terbium ion into the lithium cobaltate structure with units of fit values of 0.91, 0.85, 1.13, and 1.6 for the cobaltate lithium and doped samples with terbium. Scanning electron microscopy results reveal quasi-spherical particles with homogeneous behavior due to the chelating agent. Also, an elemental chemical analysis was carried out using energy dispersion spectroscopy to identify the amount in weight percent and atomic percent of the main elements. Today, new energy storage technology requires specific properties to meet environmental, economic, and energy needs in order to reduce the use of fossil fuels and change the use of a combustion engine for an electric hybrid one. So lithium-ion batteries are ideal candidates to achieve the goal. A battery relies on redox reaction to promote intercalation and disintercalation of lithium ions during charging and discharging of a batteries. It consists of a cathode and anode where the redox reaction takes place, an electrolyte to transport the ions, and porous and inert separator to avoid direct contact between the electrodes and prevent short circuits, and an external source for the movement of electrons. Due to its operation, cathodic and anodic materials capable of being reducible and oxidable are required. In this sense, the cathode material requires a larger type hexagonal structure with a space group 3R3M, fine, uniform, homogeneous particles without impurities. A cathodic material used since the 19th has been lithium cobaltate produced by the company Sony Energy. It presents some limitations such as the cationic mixture due to similar ion radius of each element that compose the materials, structural chains of type layers to spinel, capacity experimental, low and chemical instability, reasons why they deteriorate the battery causing irreversibility, insecurity, and low energy capacity. An alternative is to dope the structure of the cathode materials with rare earth ion to improve the electrochemical response of the battery. Doping with terbium in low mole percent concentration will allow for greater use the properties of the cathode materials doped with terbium. For this reason, when doping the structure, it will cause a local distortion in the substitution site. Partial decrease of cobalt due to the radius of the rare earth is greater than that of cobalt lithium. Structural, chemical, and thermal stability are increased in the volume of the cells for greater transport of lithium ions, which will favor the energy capacity of the battery. There are several synthetic routes to obtain lithium cobaltate, such as solid-state, co-precipitation, hydrothermal, and Solheim. The Solheim route allows greater control of the analysis condensation, pure and homogeneous product, nanometric particles, crystalline materials, and low thermal treatments. For these reasons, lithium cobaltate was synthesized and doped with terbium at low concentration by means of the Solheim pathway. The Solheim synthesis route starts from uniform particles of either metal salts or alkoxides is based on hydrolysis and condensation reactions for the formation of a solid and subsequently a three-dimensional network generated by an increase in temperature and a gelatin agent. It is the seed ahead for the purpose of the project. Nitrates were used as a precursor and acid citric for the formation of the gel. The drying was at a temperature of 110 to eliminate the remaining agents and a heat treatment at 800 during 24 hours to obtain a dense crystalline ceramic. According to the result obtained, X-ray diffraction was performed to analyze the structural properties of terbium-doped lithium cobaltate, obtaining black planes attributed to layered materials with hexagonal structure and a space group R3M. However, at a higher concentration of the dopant ion, an intermediate phase was observed, possibly generated by high temperatures at long residence times. A radial refinement was performed and the values of the cells changed as the concentration of the dopant ion increased, to which the incorporation of the terbium ion in the structure is attributed. The goodness of fit showed that the values obtained are reliable. The morphology of the particles were quasi-spherical with uniform behavior. In dark color, the lithium cobaltate is observed and in white the particles corresponding to terbium. It is worth mentioning that when increasing the concentration of the terbium ion degraded weight % in the samples. Finally, to observe the behavior of the composition in the material, an energy dispersive spectroscopy was carried out, which according to the result showed the main elements of the composition. That seed, cobalt, terbium, and carbon is attributed to the carbon type used to the analysis of the morphology in the scanning electron microscope. Crystalline powers of cobaltate of lithium doped with terbium of different concentration 0.01, 0.03, and 0.05 mol% was successfully obtained by the salt gel route. A hexagonal crystalline structure of the layer type was found with a thermal treatment of 800. The presence of the doped ion in the cobaltate of lithium structure was confirmed with the radial refinement obtained reliable values according to the goodness of fit. The morphology of the quasi-spherical particles did not change when doped. Only the average size of the particles decreased from 364 nanometers to values between 90 and 150 nanometers due to presence of the gelatin agent that allowed the growth of the particles in a uniform manner. Thanks.